Good evening, everyone. I welcome you all once again to the live session where we discuss about uh, the properties of materials, nature and properties of materials, part 3. This is a part of the NOC25-MM34 NPTEL course. And the instructor for this course, as you all know, is Professor Ashish Garg, who is from IIT Kanpur. And my name is Sairam Ramachandran, and I am a PhD scholar at IIT Bombay. I'll be guiding you through today's tutorial where we will have a quick recap of what happened over the second week. We will go revise the problem solved in week one once again. I have a new set of problems for this week as well. Along with these problem sessions, I know that professor has given something for us to solve as homework. Let's say how to identify the strain tensors for epsilon 1, epsilon 2 prime 2 prime or epsilon 2 prime, as we can generalize it, or even as gamma 1 prime 2 prime or gamma 2 prime 3 prime. We'll see how to write the tensor notations for these things. Probably the flow will be such that um, just a minute, let me share my screen. Okay, this might be the flow. We'll almost done with the introductions right now. We'll have a recap of our week one tutorials, and then probably before we'll start on with the week two tutorials as well. So week two classes, recap of the week two classes. Uh, and when we are doing this, we will try to work out those homework problems as well. Once we are done with these things, we will definitely have a very short break, like last time, a few minutes, and then we'll continue with our tutorial sessions for this week. And then I will wait for some question answers or some feedback if there is any. Okay, as I had mentioned in the previous class, there are a few deal breakers. Please stay silent and please be on mute at all times. But most importantly, I would like to have an interactive and fun class. If you have something to discuss, if you want to discuss something, please raise your hand and we can definitely have a discussion, but one at a time. If there is someone joining in late, I would personally prefer if you have your videos on so that I can observe and modify my teaching pace or my teaching methods. Let's all have fun and let's all enjoy learning. So, thank you. Uh, let's start with the tutorials of the first from the first week. Um, what I'm going to do right now is I'm actually going to share a different screen. I have a two screen setup right now. Something which makes it easier for me to um, let's say write. Just give me a minute, I just want to confirm if everyone's able to see whatever it is that I'm sharing. Yes. Yes, we are able to write, so that's one problem solved. Okay. uh, cool. Let us start solving our problems over here. Hmm. The very first problem for today from the previous class is true strain tends to be equal to engineering strain at the options are very small values of strain, small values of strain, large values of strain, and none of the above. We'll have a quick recap of what is engineering strain, the formula of engineering strain, and what is true strain. The formula of engineering strain, as we all know, I'll write engineering strain as ENGG strain equals uh, change in length by original length, where the change in length del L can also be represented as LF minus L naught by L naught. This is what, and this is represented as E, right? Um, we know the true strain, the formula for true strain, which is represented as epsilon equals ln of LF by L naught, which can also be written as ln of 1 plus E. So we saw these things in the previous class. Um, so the question coming back is true strain tends to be equal to engineering strain at what values of strain. So in the first week, professor has done this simple exercise where we compare the values of small e and epsilon, the engineering strain and the true strain, where if we see the if the value of e is very very small, let's say 0.0001, then the value of epsilon is also approximately equal to the same, which is 0.0001. When we keep coming at higher values of e, even in the case of 10 power minus 3, it is still very similar, 0.001. But when we come to much lower values, it is not approximately equal to 0.01 because the value is around 0.00995, I guess, or 95, I guess. So, and when we come to much larger values as zero point 0.1 or 1, the value for 1 is around 0.63 if I'm not mistaken, right? I can just confirm once again with the calculator. I hope you all have your calculators because this is uh, a course that is very much involved with calculators. Ln 1 sorry, ln 2 is, yeah, 0.693, sorry, ln 1.01 would be point, yeah, 99995, this is the correct one, and ln 1.1 would be 0.095. So there is not a direct relation. So uh, at very low values of engineering strain, the value of true strain tends to be similar, very similar to each other. But when we keep with increase, as we keep increasing the values of E with increasing E, there seems to be a mismatch with epsilon. Can we say that? So the value where the true strain tends to be equal to the engineering strain is at very small values of strain. Okay, let's keep moving to the next question. Strain is a tensor of rank n. So we have seen from the generalized form of the Hooke's law where sigma ij equals E into epsilon or small e, whatever you want to call it, kl. But this E is ijkl. So sigma, let's just maintain a standard notation where we'll just write E. So sigma ij equals E times capital E times capital E ijkl times strain the base kl. So strain is a second degree tensor. We just saw above. What is the what about the modulus of velocity? Once again, sigma ij equals, where this is the modulus of elasticity, or Young's modulus, as you all know. Yes, Young's modulus, and this is a fourth rank tensor, as we can say from the subscripts here, I, j, k, l. So there are four variables to deal with here. The stress strain curve is linear up to dash limit. The options are proportionality limit, ultimate tensile strength, fracture point, and entire part. Uh, we have seen details about this in even more detail in this week's classes, where if we plot the stress strain curve, we do have a, a region of linearity from say point O to point A in the case of metals and ceramics, but not in the case of polymers, as we would have observed in this week's classes. And this is primarily because uh, this is the region of elasticity, and this is applicable only till the proportionality limit. So the answer for this question is proportionality limit. The next question is, what is the average linear strain produced when a solid bar is extended from 1 meter to 1.5 meter? What is the formula for average linear strain? Average, let me try and use a new color. Linear strain equals del L by L naught, which is LF minus L naught by L naught, which is basically the final length minus initial length by the initial length. Here the initial length is 1 meter because this 1 meter bar is extended to 1.5 meters, so the final length will be 1.5 meters. So when we check the strain E, which is 1.5 minus 1 by 1, which gives us the value of 0.5. So the answer is zero point 0.5. Moving on to the next question. For an isotropic, homogeneous, and elastic material obeying Hooke's law, the number of independent elastic constants is. So under Hooke's law, we know what is Hooke's law. E. We saw the tensor version of Hooke's law at multiple points during this class. The answer to this question is, wait a second, let me just confirm. Yes, it is 3. Among the following materials, which one doesn't follow Hooke's law? Wow. Um, but what are the conditions for Hooke's law? It is the conditions for Hooke's law are very small values of strain, and we should have an linear elastic region. In the case of steel, copper, or aluminum, which are metallic materials, we know for a matter of fact that we will have a linear region followed by a curved region. But we have also seen in this week's lectures that in the case of polymers or rubbers or elastomers, it is very hard to come by such a linear region. So what we end up having is that we end up having a long non-linear region, or but which is still elastic in nature. So all these are for polymers, elastomers, rubbers. These are classes of materials um, which don't follow Hooke's law, that do not have a linear elastic region, and they don't follow Hooke's law. Okay, so the answer to the question is rubber. We'll move on to the next question. Which of the following is a composite material? Uh, Nylon is a polymer, steel is a metal, mica is not the answer. So the only possible answer that could be a composite material is wood. Why is wood a composite material? Because it has a substrate and it has uh, fibers, wooden fibers running through its cross section in different directions so as to provide more support and stability. Which of the following properties is dimensionless? Which of the following properties is dimensionless? Uh, well, we know that surface tension has a dimension, kinematic viscosity has a dimension, bulk modulus has a dimension, as we are going to see it later. Bulk modulus dimension is GPa. So the only thing which is dimensionless, because as we know it, strain is change in length by L naught, and if we take the uh, units of it, this will be meter, this will be meter. When meter gets cancelled, we have a dimensionless quantity. So the answer for this is strain. If the radius of wire stretched by a load is doubled, then what would happen to its Young's modulus? This is a very interesting topic that was touched upon the first week and was elaborated in the second week as well. Young's modulus is one such quantity which is known as intrinsic quantity. We look at this in detail when we talk about atomistic aspects, or the when you go through the when you take a recap of the notes of lectures 8, 9, and 10 of this week, probably more than 9 and 10 of this week. Young's modulus is a quantity which is known as intrinsic in nature, which means that till it does not matter what is the heat treatment or the processing that a material undergoes, the property the materials, unless and until the composition remains same and it does not change, Young's modulus is going to remain the same. Only when there is a change in the composition, or more fundamentally, only when there is a change in the nature in which atoms are bonded in this particular material, uh, would there be a change in its Young's modulus. Till the time the pre-processing and post-processing nature of bonding of the atoms of this material remains constant, the material would have the same Young's modulus without any change to its Young's modulus. So the Young's modulus will remain unaffected. Shear stress is defined as sigma ij equals Fi by Aj, and we all know that Fi by Aj is option A. Okay, we saw the answer to this question. The answer should have been 17 MPa in my opinion, and so yeah, this should be the correct one. Uh, I1 equals sigma x plus sigma y plus sigma z. So it should be 10 plus 15 minus 8. So it would be 25 minus 8, which should have been 17 MPa. Okay. Which of the following is true in a general stress tensor? So sigma ij is not equal to sigma ji for I equal to j. No, sigma ij equals sigma ji for I equals phi and I not equal to j. We know that that is going to be the true. That is going to be true. So this is the right answer. Consider transformation of stresses from one orthogonal system to the other. Assume that the shear stresses were zero in the original system. The stress tensor for a new axis system will be. So they are basically asking us to find sigma 1 prime 1 prime. As we know, the formula for this is n is equal to 1 2 3, m equals 1 2 3, lim ljn, uh, sigma mn. Here 1 prime is the I and j values. So, and we also know from the question that assume shear stresses were zero. So which means Sigma ij equals sigma ji, oh sorry, rather sigma mn. Sigma, any values of sigma mn equals sigma nm is 0. So till the time m is not equal, if m is not equal to n, if m is equal to n, that's a different story altogether. So we'll start working on this. We know I equals 1 bar, I equals 1 prime, j equals 1 prime. We'll have to vary m and n. So sigma 1 prime equals L1 prime 1, L1 prime 1, sigma 1 1 plus L1 prime 1, L1 prime 2. So across the row we will keep changing n, and across the rows we will keep changing m. L1 prime 1, L1 prime 3, sigma 1 3. So how am I writing 1 2 and 1 3? So we know that the sorry we know that this is m and this is n. Whatever the are the subscripts for m and n, I'm taking sigma mn. Similarly, this will be, now I'm changing the values of m for the first time. So this one will become 2 here. Now this L values are going to remain the same exactly as we had over here. 1 prime 2, sigma, sorry, 1 prime 1, sigma 2 1, 1 prime 1, 1 prime 2, sigma 2 2. I'm sorry once again. L1 prime 2, L1 prime 3, sigma 2 3 plus L1 prime 3, L1 prime 1, sigma 3 1 plus L1 prime 3, L1 prime 2, sigma 3 2 plus L1 prime 3, L1 prime 3, sigma 3 3. As you all know, sigma mn equals sigma nm equals 0 if m is not equal to m. So everything, only sigma of, only values of, okay, amazing, only values of sigma 1 1, sigma 2 2 and sigma 2 3, sigma 3 3 are not 0. Every other value is 0. So we can write 0 0 0 0 0 0. This makes our life easier. Only the values across the diagonal are not 0. So sigma 1 prime equals sigma 1 prime equals L1 prime 1, L1 prime 1, sigma 1 1 plus L1 prime 2, L1 prime 2, sigma 2 2 plus L1 prime 3, L1 prime 3, sigma 3 3, and that is our final answer. Do we have this option? Yes, this is option D. Okay, okay, we are at the end of the first week's tutorial classes. I will have this blank page for now. Um, I'm planning to have some more additional uses for the same. But right now, I would like to go back to the first week's classes, the second week's classes. We'll quickly go through all the class notes right now from the second week, and then uh, when and wherever I feel there is a need that we can probably solve. We can probably solve the homeworks that professor has given. We will we'll take that up and we'll do those problems as such. We just finished revising uh, the week one tutorial questions. Uh, we'll have a quick recap of the week two lecture notes, and then now I know for a matter of fact that so professor has given some homework questions, probably in lecture 7 and 8, probably in lecture 9 as well, in 6 as well. We'll try to solve as many as possible. I have noted down two or three problems specifically where we are expected to um, try and solve the strain tensor notations, epsilon 1 prime 2 prime, or gamma 1 prime 2 prime, or epsilon 2 prime 2 prime. We'll try to expand on those problems. So right now we know if the principal stresses are sigma 1, sigma 2, sigma 3. This can happen only when the principal axes are 1, 2, 3. Principal axes are such that it is 1, comma 2, comma 3. Um, Sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equals 0. This is the equation that is when we solve these things, we've given if we are able to find out I1, I2, and I3, which are invariants, using the formulas given below, we get the values of sigma 1, sigma 2, and sigma 3. This applies to when all other shear stress components is 0. So this is applicable principal stresses or principal axes are only when there is stresses applying only along those principal axis and there is no shear stresses, there is no stresses along any other axis. Okay, we also have went through the definitions of true and engineering strain. Epsilon equals ln LF by L naught. Uh, this is the definition of engineering strain, true strain, and the formula for engineering strain is E equals LF minus L naught by L naught. We had solved a few problems just, just before this. And what are the differences between true strain and engineering strain? As As we'll see in the example below, we'll try to resolve the example once again a little bit more slowly. True strains are equal and opposite in direction. So which means as we have an example here, if we move from L1 to 2L1 with tension and we compress it back again to L1 dimension, the strains involved between in this journey from L1 to 2L1 and then to L1 to L1 and then or the entire thing, these are going to be these are going to be same, or let's say it has additive and commutative properties. The true strain follows additive. True strain follows additive properties or additive nature. But engineering strains do not have these things, and they're not just equal but they are opposite in direction. So when we go from L1 to L1, it has some value of true strain, but when we go from 2L1 to L1, which is a compression, it will have numerically the values will be same, but there will be a difference in sign. So if this is positive, the compression will be negative. If the compression is positive, the tensile will be negative. But we know that is not the case. It is always positive in compression, in tension, and negative in compression, uh, which is quite obvious from the formula, which is ln of LF by L naught. If the final length is smaller than the initial length, which is a value which is less than 1 in the case of a fraction, then ln of a fraction less than 1 is negative number. We can also see this volume change is related to some of these three strains. Um, this is available in a second example. Verify the tension compression equivalence. So let us try and solve this problem once again. I'll bring a note here. Here the given values for us are L naught equals 1 meter, and upon tension, when we apply a tensile load to this specimen, it reaches to a value of L1, which is 2 meter in length, and then upon compressing this, it comes back to a dimension of 1 meter. Am I right? Yes. Moves back to a length of 1 meter. So we'll try and compute the true strain and engineering strain components of all these things involved. So there are two steps. Step 1, this is step 1 and this is step 2. So we'll start with true strain for step 1. So the true strain for step 1, as we know, epsilon f equals ln of Lf minus L naught, or in this case equals ln of L1 by L naught. Here L1 is 2 of 2 by 1, which is ln 2, which is 0.693. Amazing. Now we'll compute the same strain for step 2. Here epsilon of compression. Okay, this is in tension, this is in compression, equals ln of Lf by L naught. What is the Lf and L naught in compression? Lf becomes 1 meter, and then L naught is actually 2 meters in this case of compression. So ln of final is 1 meter and the initial is 2 meters. So this actually becomes 1 by 2, or we can say 2 power minus 1. And then we know if ln of a power x power minus 1 is minus ln x, so which is minus 0.693. I'll write it again. Epsilon in tension, the true strain during tension is 0.693, and epsilon during compression, the true strain during compression is minus 0.693. These are equal in value but opposite in direction. Okay, amazing. Now let us try and compute the engineering strain. So the engineering strain over here, E is given by Lf minus L naught by L naught. In the first case, E1 equals Lf is 2 meter minus 1 meter by 1 meter, which is given 1. So E1 equals 1. What about the second case? In second case, or E2 or EC equals, the final length is 1 minus the initial length is 2, and the initial length again here is 2. So here is minus 1 by 2, which is minus 0.5. E2, E1 is 1 and E2 is minus 0.5, right? So if we see here, there is E1 and E2 are not even close to each other, not even same as each other, even in terms of numerical value. Um, and that is a huge, there is a huge difference that we are observing over here. Okay, so from this we can again reiterate the fact. From here, once again, we can reiterate the fact that true strain is equal and opposite in direction for tensile and compressive loads for the same. I mean, if you are going to apply different loads for tension and compression, and if we are trying to compare the loads during tension and compression for different loads, that is obviously going to be different in the values of true strain. In such a case, is definitely going to be different. When we are applying similar loads in tension and compression, the true strains are going to be equal in for both numerically, but they are going to be in opposite directions. Okay, we can see one more thing. If we consider the initial to final L0 to L0 transition, if we compute epsilon for C, which is ln of LF by L0, which is ln 1 by 1, which is ln 1 is 0. E final, let's say, E final can be taken as, can, shall we compute EC plus epsilon, not E, sorry, epsilon C plus epsilon T, which is minus 0.693 in the case of compression plus 0.693 in the case of tension, which cancel out and then it comes back to 0. So E final equals epsilon T plus epsilon C. As we know, this is additive in nature. This follows the rule of additivity. And yeah, but this is not going to be the case in the case for um, true strain, so engineering strain, because E might be 1 minus 1 by 1, which is 0 by 1, which is 0. But if we are trying to compute E1 plus E2, it is going to be 1 minus zero point 0.5, which is zero point 0.5. And it is not the same as the E total, right? So the engineering strain does not follow the rule of additivity either. Okay, we'll move on. We'll have this notes. If we want to make additional notes in some other case, we can take it back. Yeah. Okay. We saw about volumetric strain. So the third rule was that in the case of a volumetric change is equal to 0, then epsilon x, epsilon y, and epsilon z, the summation of epsilon x plus y plus z equals 0. But ex plus ey plus ez is not necessarily 0. Um, we have I have earmarked a few more important problems for us to try and work out. If we do have some time at the end of this session, we'll definitely come back. We'll definitely revisit this particular topic. Uh, yes. So let us, for now, let us move on. So this was after this we started talking about what happens when we apply very small strains, and when we have an addition of an element called a shear strains in the system. How do we apply transformation of axis to the small strains and shear strains to the system? What are going to be the values? What is going to happen in the case of a 3D body? Um, so mathematically, if we saw that epsilon ij equals 1 by 2 gamma ij, uh, we have the derivation of this is in the data book, or even in the book that professor had suggested. You can go through it. Transformation of axis to strains, very similar to uh, transformation of axis for stresses. Here, professor had solved for epsilon 1 prime 1 prime or epsilon 1 prime. We will try and solve for professor has also solved the equation for epsilon 1 prime 2 prime or gamma 1 prime 2 prime, which is again we have to remember that in the case of stress sigma 1 prime 2 prime uh, equals tau 1 prime 2 prime, but in the case of epsilon 1 prime 2 prime is not the same as gamma 1 prime 2 prime, because epsilon 1 prime 2 prime equals 1 by 2 gamma 1 prime 2 prime. Okay, sorry for writing it on top of this notes. Okay, right. What do we have for homework? We'll try to solve at least two of these things. We'll try to solve epsilon 2 prime and we'll also try to solve gamma 2 prime 3 prime. Okay, okay. We will expand this. Yeah, we already have this. We'll continue with the same thing. So the question right now that we are trying to solve right now is what is going to be the expression for epsilon 2 prime 2 prime? We know that summation m equals 1 to 3, n equals 1 to 3. This is L2 prime m, L2 prime n, epsilon mn, right? This is once we are able to expand this, we are going to be able to solve for the final answer of epsilon 2 prime 2 prime. Sorry, here epsilon 2 prime 2 prime equals, we'll start with here again, as I said, changing n, changing m, L2 prime 1, L2 prime 1, epsilon 1 1 plus L2 prime 1, L2 prime 2, epsilon 2 1 plus L2 prime 1, L2 prime 3, epsilon 1 3 plus L2 prime 2, L2 prime 1, epsilon 2 1 plus L2 prime 2, L2 prime 2, epsilon 2 2 plus L2 prime 2, L2 prime 3, epsilon 2 3 plus L2 prime 3, L2 prime 1, epsilon 3 1 plus L2 prime 3, L2 prime 2, epsilon 3 2 plus L2 prime 3, L2 prime 3, epsilon 3 3. Okay, this is just an expansion of L2 prime m, L2 prime n, epsilon mn, when where we are doing the summation of m equals 1 to 3, n equals 1 to 3. Now we know the condition for this is epsilon mn equals epsilon nm when m is not equal to n. So from this we can get epsilon 1 2 equals epsilon 2 1, epsilon 1 3 equals epsilon 3 1, and epsilon 2 3 equals epsilon 3 2. We know these things for sure. We also know that These are not 0 in this particular case. We are just trying to solve it. We also know epsilon ij equals 1 by 2 gamma ij, right? Where I is not equal to j. Okay, cool. Now when we know this, a small mistake here, 1, 2. Okay, okay, we'll come back. Epsilon 2 prime 2 prime can be rewritten as L 2 prime 1, L 2 prime 1, epsilon 1 1 plus, or we can just write this as a square. L 2 prime 1 square epsilon 1 1. I'll just write epsilon 1 1 as epsilon 1 plus L2 prime 2 square as epsilon 2 plus L2 prime 3 square into epsilon 3 1 1 2 2 3 3 for easier identification. Okay, now I think we can combine. um, just let me know if this makes sense to you. L2 prime 1, L2 prime 2, epsilon 1 2 plus L2 prime 2, L2 prime 1, epsilon 2 1. I'm combining these two as one term. Why? Because these are same. Okay, I'm similarly combining L2 prime 2, L2 prime 3, epsilon 2 3 plus L2 prime 3, L2 prime 2, epsilon 3 2 plus L2 prime 1, L2 prime 3, epsilon 1 3 plus L2 prime 3, L2 prime 1, epsilon 3 1. I am combining. So how many? We had 9 terms when we expanded the tensor form. Now we have 1 2 3 4 5 6 7 8 9. We still have those 9 terms intact. So whatever we have written seems to be correct. So when we combine, as these two are equal and these two seem to be equal, so this becomes 2 into this particular term, 2 into this term, 2 into this term. But now we know that epsilon 2 1 equals 1 by 2 gamma 2 1. So when I rewrite this, 2 prime equals L2 prime 1 square epsilon 1 1 plus L2 prime 2 square epsilon 2 2 plus L2 prime 3 square epsilon 3 3 plus 2 into L2 prime 1 L2 prime 2 epsilon 1 2 plus 2 into L2 prime 1 2 prime 2 L2 prime 3 epsilon 2 3 plus 2 into L2 prime 1 L2 prime 3 epsilon 1 3. Now as we know here, as we can see from here, so now we replace epsilon 1 2 equals 1 by 2 gamma 1 2, epsilon 2 3 equals 1 by 2 gamma 2 3, and epsilon 1 3 equals 1 by 2 gamma 1 3. So when we do that, epsilon 2 prime becomes L 2 prime 1 square epsilon 1 1 plus. So when I replace epsilon 1 2 with gamma 1 2, the 2 2 gets cancelled and we have finally have just the gamma terms. plus L2 prime 1 L2 prime 2 gamma 1 2 plus L2 prime 2 L2 prime 3 gamma 2 3 plus L2 prime 1 L2 prime 3 gamma 1 3. I think this agrees with uh, what is already uh, present in the case of this is in line with what we had already written for gamma 1 prime 2 prime. So if we see here gamma 1 prime 2 prime, it is written as 2, no, sorry, the previous equation, yes. Epsilon 1 prime is epsilon 1 prime square epsilon 1 prime 2 prime square epsilon 2 plus epsilon 1 prime 3 square epsilon 3 plus L1 prime 2 L1 prime 3 gamma 2 3 plus L1 prime 3 L1 prime 1 gamma 3 1 plus L1 prime 1 1 prime 2 gamma 1 2, which is, so we have 1 2 3 4 5 6, we have 6 terms over here, and even in our equations we have the same 6 terms. So we were able to find out the expression for epsilon 2 prime. Amazing. Next, what was the next topic that we had to work out? So I hope you understood how we derive the equation for epsilon 2 prime 2 prime. Now let me change my color. I'll go with this particular color. The next question was to find out gamma 2 prime 3 prime. We'll use the same formula, summation L2 prime M L3 prime N sigma M epsilon Mn. Can you just give me 1 second, please? I just need to take a sip of water. Let us start with this particular question, which is to find the expression for gamma 2 prime 3 prime. Or we can also say epsilon, but epsilon 2 prime 3 prime and gamma 2 prime 3 prime are not the same. So we'll stick with gamma 2 prime 3 prime, which is the shear strain associated with the two new axes 2 prime and 3 prime. Okay, gamma 2 prime 3 prime. We'll first try and find out the expression for, though this is not the equation. Um, this is the formula for epsilon 3 2 prime 3 prime, and then we know that epsilon 2 prime 3 prime equals 1 by 2 gamma 2 prime 3 prime. So when we need to find gamma 2 prime 3 prime, it is basically 2 into epsilon 2 prime 3 prime. So once we find out the epsilon of epsilon 2 prime 3 prime using this formula, we just have to multiply that equation by 2 to get gamma 2 prime 3 prime. So that's what we are going to do right now. That is what we are going to try and do right now. So let's get started. Epsilon 2 prime 3 prime equals, was the very first equation, L2 prime 1 L3 prime 1 epsilon 1 1 plus L2 prime 1 L3 prime 2 epsilon 1 2 plus L2 prime 1 L3 prime 3 epsilon 1 3 plus L2 prime 2 L3 prime 1 epsilon 2 1 plus L2 prime 2 L3 prime 2 epsilon 2 2 plus L2 prime 3 L3 prime 3 epsilon sorry epsilon 2 3 plus L2 prime 3 L3 prime 1 epsilon 3 1 plus L2 prime 3 L3 prime 2 epsilon 3 2 plus L2 prime 3 L3 prime 3 epsilon 3 3. Okay. See, I know I have also made a mistake, and this might be very confusing when you try to do it for the first time. Try to practice the problem that professor did in class along with him. Try to solve the problems that I have done here along with me, and then try to solve it on your own. The only thing that you have to keep in mind is when you solve these problems, the I and j value, you should not even be bothered about what is in I and what is in j. You'd only be worried about what is m and what should be the value, what should be the values of m and n. When we vary the values of m and n properly, n across the row, n across columns or m across the rows, we will be able to write this entire tensor accurately without any mistake, without any problem at all. So once we have this, the same rules apply again, where we know epsilon 1 2 equals epsilon 2 1, epsilon 1 3 equals epsilon 3 1, and epsilon 2 3 equals epsilon 3 2. We know these things for sure. One problem that we will have that we were able to do earlier was we could, so along the diagonal terms in the previous equation epsilon 1 2 2, we were able to combine those two and make it square. So because we had um, because we had an expression like L2 prime 1 L2 prime 1, we could make this as L2 prime 1 square. Similarly L2 prime 2 L2 prime 2, we can make this L2 prime 2 square, and because we had L2 prime 3 L2 prime 3, we could make this L2 prime 3 square. We would not be able to do anything of that sort here because we don't have any such similar terminologies at all. So we will have to use this equation and what we know here, this particular equation, to try and solve this. Epsilon 2 prime 3 prime equals, I am going to separate the diagonal terms first. Have it with me closer. L3 prime 3 prime 1 epsilon 1 1 plus L2 prime 2 L3 prime 2 epsilon 2 2 plus L2 prime 3 L3 prime 3 epsilon 3 3. These are my diagonal terms. So I'm going to start. So we know here from from the previous equation, we know that epsilon 1 2 is same as epsilon 2 1. So I am going to take that particular factor out, which is epsilon 1 2 out of the equation, and what we have is, if I take 2 into epsilon 1 2, we have, so no sorry, we have L2 prime 1 L3 prime 2 plus L2 prime 2 L3 prime 1 plus, so you know that epsilon 2 3 and 3 2 are same. Epsilon 2 3 into epsilon 2 prime 2 L3 prime 3 plus, sorry, let me get this. L2 prime 3, L3 prime 2, epsilon 3 2 is what we have taken out, plus L2 prime 2, L3 prime 3, epsilon 2 3, plus epsilon 1 3 into, we have remaining, these two factors will be combined. So which is L2 prime 3, L3 prime 1 plus L2 prime 1, L3 prime 3, right? We have taken out these equations from here, from now. Okay, from here we can change to the term epsilon ij equals 1 by 2 epsilon gamma ij. When we substitute this here, gamma 2 prime 3 prime equals for I not equal to j, which means that epsilon 1 1, epsilon 2 2, and epsilon 3 3 will remain the same. We'll have a 2 multiplied by this, so 2 into L2 prime 1, L3 prime 1, epsilon 1 plus L2 prime 2, L3 prime 2, epsilon 2 plus L2 prime 3, L3 prime 3, epsilon 3 plus we'll have 2 into 1 by 2 gamma 1 2 into L2 prime 1, L3 prime 2 plus L2 prime 2, L3 prime 1 plus, so we know that when we convert epsilon 1 2 into 1 by 2 gamma 1 2 and multiply 2 from the here, 2 2 gets cancelled, so I'll not do the same thing again for 1 2 epsilon 2 3 and epsilon 1 3. I'll just write the equation directly. Gamma 2 3 into L2 prime 3 L3 prime 2 plus L2 prime 2 L3 prime 3 plus gamma 1 3 into L2 prime 1 L3 prime 3 plus L2 prime 3 L3 prime 1. So this is the equation, this is the overall answer for gamma 2 prime 3 prime. Okay, I hope you are able to understand this. Uh, if you are able to understand, so right now we have, professor has solved equations epsilon 1 prime 1 prime and epsilon 1 prime 2 prime. We have solved, or rather gamma 1 prime 2 prime. Now we have solved epsilon 2 prime 2 prime and gamma 2 prime 3 prime. We have solved these two equations. So we have solved four different expressions to write this in tensor form. Hopefully this is adequate to uh, adequate practice. We'll go back to the no, the week's class notes. Um, Professor also asked you to think about simple problem of very small strains versus very large strains. What was going to happen when we work, when we try and um, when we deform a particular thing in the x direction along the x prime y, where the x is displaced by dx, which is 0.02, and y is displaced by dy, which is again 0.02a. What is going to be the strain? So let us calculate. So we can calculate the length of the diagonal of this new shape that is formed, and then you can use the formulas epsilon 1 and epsilon 2 as well, which is given here. What is the uh, length of the diagonal? So we know this still subtends a 90-degree angle. So we know this still subtends a 90-degree angle uh, to the x-axis. Um, Initially, if this were a and a, we know that the angle subtended between the hypotenuse between the diagonal x prime and the x-axis is 45 degrees. But right now we know that it is not going to be the case. It has been displaced by a very small theta, where tan theta can be simplified as theta. Um, we can still, so let's say if this, assume this angle to be theta, then this is, we know that obviously this is 90 minus theta. Try, this is x prime. Try solving for cos theta and sin theta. Um, we know cos theta is adjacent by hypotenuse, which is, so in this case it is 1.02a by x prime, and then x prime becomes 1.02a by cos theta. Same with sin theta, we don't know, so which is 0.98a by y prime, so y prime becomes 0.98a by sin theta. So we know the values of cos theta and sin theta, so x prime and y prime right now. Calculate strain using this particular diagonal of this diagonal. Um, so you can use these values, and then you can try and work out the length. We pretty much know the length of this right now, so you can try and work out the details of the same. So what is going to be the strain involved along the x prime direction? Uh, so what is going to be the strain involved along the y prime direction? So basic, no. So these are the x prime and y prime lengths. You know the length of, so you know the equation for x and y, which is a by cos theta and a by sin theta. So if you know the x and y, you can calculate the distance between two the new distances, difference between x prime and x and y prime and y. When you're able to do this, this gives us the geometric value. You can also use this particular equation given here, try to solve the same. We will be able to solve it much more easily. But when we know for sure that, when we know that there is a huge displacement, and when we try and solve these using the transformation of axis that we have been discussing so far, we will be able to find out that this is not going to be possible for us to equate through the diagonal and using the strain equations. This is a homework again left for you to solve. Uh, so again, just a recap of what we had to do previously. So you can see when we have to apply transformation of axis to the strain tensors, when the tan theta equals delta by L naught, and then for very small values of theta, as we saw in the example just given above, tan theta can be equated to theta alone, and the theta basically becomes delta by L naught. So after the transformation of strains, we moved into the theory of elasticity. This is a very fundamental aspect of elasticity, very important that we try and learn this. What is elasticity? It is an elastic deformation on materials. We know that it is reversible. All materials exert, so they come back to its original dimension, they come back to its original shape. Materials of all kinds show these type of features. We know all these factors. So all crystalline solids, be metal, ceramics, or any other categories, they definitely show this sort of a behavior. Um, and they show very small, but they show very small elastic strains though. Uh, Materials like polymers, elastomers, rubbers, they show much higher elastic strains. So this is what we see in the sigma versus the stress strain plots as well. So in the stress strain plots, for metallic and for ceramic materials, we see this sort of nature a very small area under the curve for. I'll not use the term very small area under the curve because the value of these stresses can be pretty huge even in the case of metals and ceramics, but this value might be very small in the case of polymers. But let's say the uh, linear region between the basically the length OA, or the angle at which OA stands might be very sharp, very high for metals and ceramics. But in the case of OA for the polymers, this is for most crystalline solids, and this is for polymers. It's not a very steep curve. It gradually tends to a, and it does not follow a linear path. But even amidst all these problems, it still follows. It is still elastic in nature because when we leave out, if we are inducing stresses from say 0 to say sigma 1, sigma 2, sigma 3, sigma 4, if we release the stress at even at sigma 4, it almost comes uh, back to the point 0 in terms of the elongation. Uh, we saw the generalized form of Hooke's law. Sorry, we saw the generalized form of Hooke's law. We also saw what are the other methods of measuring modulus of elasticity, acoustic measures. So where we saw using the velocity of sound in a material, we can find what is the modulus of elasticity. What this tells us again is that the modulus of elasticity is dependent on the bonding between atoms. So till the time the bonding nature of bonding and the composition of bonding remain same, the modulus of elasticity, which means when all the other microstructural and atomistic features remain the same, the velocity of sound propagation in the material is going to remain same. Uh, you all of us would have read about the nature and properties of sound in our say seventh or eighth standard classes, where sound can propagate both as particles or through a medium as waves. Um, Imagine sound propagates through a particle. So there is atoms in a material are going to be constantly vibrating, but when there is an external sound wave, which is basically an external sound energy, which comes and interacts with the vibrating atom, which is vibrating about its mean position, the external sound wave pushes this atom, and this keeps propagating through other atoms as well. When the distance between these two atoms and the bond between these two atoms remain of similar strength and of similar distance, the sound wave is going to propagate at the same speed, at the same velocity through the entire material. Only if we induce some defects or any other characteristics where the composition of the material is going to change, or we are going to introduce point defects such as oxygen vacancies or slip systems or any of these things, or cracks from a microstructural perspective, will we observe a change in the velocity of sound. Um, and till the time the modulus of the material is going to remain exactly the same, and there's going to be no change of the modulus of materials. Apart from the modulus, a few other um, we saw a few other very important properties as well. So it's not just the modulus of elasticity. We can also see shear modulus. Shear modulus representing as G is the shear stress by shear strain. We also have the bulk modulus, which is the hydrostatic stress component divided by the fractional volume change, which is given here by kappa, which K, capital K, which is sigma hydrostatic by uh, change in volume, fractional change in volume, which is del V by V naught. Um, uh, in this, amongst these three, Young's modulus, shear modulus, and bulk modulus, uh, the Young's modulus, this plane strain, the plane stress, uh, or the hydrostatic stress can be tensile or compressive in nature. The final component, the most important component of all, is the Poisson's ratio, which is represented by nu. Nu is the ratio of the transverse strain to the lateral strain, and which is given by minus Ey by Ez. And the general range of this Poisson ratio seems to be around 0 to zero point 0.5. For metals, it's typically in the order of 0.33, ceramics in the order of 0.25, polymers in the order of zero point 0.4. So these are when we do experiments, when we do a normal axial strain experiment, which is basically a tensile test, we get the values when we have a tensile specimen like this, which is called a dog bone specimen. So obviously, as we can see from the image, you can all see that this looks like a dog bone, which we have seen in cartoons and etc. So when we when we pull these two ends apart, we are basically giving an axial strain, axial stress. This is called as the tensile stress. Shear modulus, we can observe shear modulus, how do we apply shear stresses? You have something called as flexural and torsional as well. So using tensile stress, flexural stress, and the torsional modulus, uh, shear is basically when one rubs against each other. So when I so if I have something of if let's say assume a book is the perfect example. I have a surface of a book. If I push the book like this is my finger. I have my finger on top. I have one more finger at the bottom to hold one more, yeah, one more hand on the bottom to hold it. I take my hand, I slide it across the surface of the book. As you can see here, I'm not compressing, I'm not pulling this book, I'm not pulling this book like this. I'm sliding my hand along the surface of the book, and as you can see here, there is some change happening to the very edge of the book, like we see over here. The same with this case. You can see there is some changes happening to the other end. If I, depending on the direction I move, this this type of stress that is applied to materials is called as shear stresses. And when we plot shear stress versus shear strain, the slope of the linear region is the shear modulus. The slope of the curve draw between the slope of the linear region between the hydrostatic stress and the fractional volume change basically gives us the bulk modulus. When we assume elastic modulus to be isotropic in nature, which means it is equal and homogeneous in all directions, then we don't necessarily need to know all four of those quantities. Even if we know two or three of those quantities, we will be able to compute the remaining. So these are relations between the various. So the bulk modulus can be K is E by 3 into 1 minus 2 gamma, G is E by 2 into 1 plus gamma, and gamma, it's a nu, sorry. K is E by 3 into 1 minus 2 nu, G is E by 2 into 1 plus nu, and nu is E by 2G minus 1. So these are three very important relations between these things. Um, Professor was talking about lateral strains across dimensions and deriving the general form of Hooke's law. Um, uh, Once again, in detail about the general form of Hooke's law and how we can use the generalized form of Hooke's law to arrive at the various relations that we saw earlier. G equals E by 2 plus 2 into 1 plus gamma. This is K equals E divided by 3 into 1 minus. So there is one small mistake here. Here it should be kappa K equals E by 3 into 1 minus 2 nu. Sorry. I'll use a better color. Here it is, that's just while writing, so just make sure that you add it is 1 minus 2 new, know the differences. And when we combine the equations, two equations, nu equals e by 2g minus 1. So we saw how how to measure, how do we basically understand these quantities. We also saw the various general forms of Hooke's law. The final topic was the atomistic origin of elastic modulus and the differences between um, the various types of bonding, which is the primary bonding of ionic, covalent, metallic bonding, and the secondary bonding type of hydrogen bonding, van der Waals bonding, all these very weak weak bonds. When we talk about atomistic nature of elasticity, it all comes down to how is the nature of the well in the potential energy versus distance plot. The very simple example of why we have an attraction and a repulsion over here is when we have two atoms have a very strong core surrounded very strong core which consists of consists of protons and neutrons, which has a positive charge and a neutral charge, along with a cloud of electrons with a negative charge. When two atoms are near each other, the external cloud is filled with negatively charged electrons. When we try and force two atoms close to each other, there is going to be a part where the two electron clouds are going to repel each other, because as we know from magnetism, as we know from electricity, like poles or like charges repel each other. Um, so that we are going to face an extreme force of repulsion beyond a certain limit. Um so the the positive potential energy is because we need to supply energy from outside for us to bring two atoms close to each other, close to each other, close to each other. However, um, the the nucleus and the electron cloud have its own attraction towards each other, because those are oppositely charged. And when we give enough distance, but at the same time, this force of attraction between the positively charged nucleus and the negatively charged electron cloud is only will only stay strong, or will only hold good till a certain distance. When there are electrons in, say, let's say, we know, when we talk about electronic shells, we have the K shell, L shell, M shell, and N shell. When we have a very small nucleus, but when we have electrons which are excited and which are in the M shell or the N shell, then let's say K, L, M, and N. For the same size of nucleus, if we are able to excite an electron from K shell to M shell, L shell, K to L, or K to M, uh, then the force with which the nucleus can attract the electron in the M shell is going to weaken. So the negative force of the negative potential that we see here in the bottom of the screen, this basically talks about the attraction between uh, the positive and the positive nucleus and the negative electron, the forces, the repulsion between the two electron clouds or the neutron densities. So only till a certain distance will there be an extreme repulsion, and we need to provide a very high potential for it to overcome this and then come closer. Similarly, only at very short distances from the nucleus will the nucleus have a very strong attraction towards the electrons. So that which means that is the point where we have the highest uh, uh, stored energy. And as we move away, say, let's say L shell, M shell, N shell, the potential energy that the nucleus has, or the power of attraction that the nucleus has towards the outermost electron, is going to weaken and weaken and weaken. So that is why we have this sort of a nature of plot where um, yes, and Professor very rightly tried to derive how do we um, measure modulus of elasticity as the slope of the force with respect to distance curve in the potential energy versus distance curve. And we tried to solve some problems as well. Finally, we came to effect of bonding on the modulus of different materials, and we saw examples of different materials. As we can see here, when we with when we grow across the periodic table, say from hydrogen to helium to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, uh, and finally neon, um, hydrogen, lithium, sodium. I guess it is sodium. Okay, whatever it is. Uh, so when we go across the table, we see that um the bonding keeps increasing, increasing, increasing. We can say the strength of the bonds keep increasing, and so does the elastic moduli. It's also keep increasing across when we move from the left to the right of the periodic table. And as we saw below, when we move from when we move down the periodic table, the modulus decreases because we are talking about the ease with which the outermost electron can be removed from a given nucleus, from a given atom. So in the case of very large atoms where the nucleus is their outermost electron is shielded from the nucleus by the innermost shells, where it is extremely attracted. The innermost shells are extremely attracted to the nucleus, and the power that which the nucleus can exert on the outermost shell is becomes lower. Um, so which tells us that the E down the periodic table is 10 degrees decreases. Okay, this tells us if we understand how bonding takes place between different materials and uh, what is the nature of bonds, etc., we'll be able to understand the atomistic nature of elasticity. This is a very simple concept. If you are able to visualize what I'm talking about, if you're able to visualize what is being mentioned here, this should be a very easy task. Okay, we are done with the recap of week two. So now, uh, let me take a 2-3 minute break. I guess we have around half an hour more for our session to end. I'll just take a 2 minute break where I'll just have some water and then we can continue. The time is around 8:36 now. We'll try to wrap up um, the tutorial for this week, the next 30 minutes. But let me take a short break, very short break. Let us continue with this week's tutorial session. The transformation of axis for strains is applicable for small strain values, moderate strain values, and large strain values, or any value of strain. This was discussed in the very first and second, or the sixth and seventh lectures of this course, where the transformation of axis is applicable for only for very small strain values, where say this is theta, this is delta L naught, tan theta equals delta by L naught. I've drawn it to be a lot bigger, but let's assume that it is very small. Tan theta equals delta by L naught from basic mathematics. But for very small values of theta, tan theta is very similar to theta. This is also mathematical in nature. Um, so we can equate theta is approximately the same as delta by L naught. Okay. So this is appropriate only for very small values of theta, or very small values of uh, strains. So this is applicable only for small strain values. Moving on to the next question. If the composition of a material remains the same, then the change in processing conditions may lead to change in tensile strength, ductility, elastic modulus, and toughness. So what does this mean? Um, when we change, okay, let us come to, let us take this example. So uh, in one of the classes in this week, professor had mentioned the grains, if the grains are along different directions, polycrystalline in nature, which means that they might be oriented in so many different directions. And um, when we undergo a change in processing by, let's say, rolling or forging or heat treatment, or whatever may be the thermomechanical treatment, whatever may be the case, this could start to have a relative orientation of sorts, where most of the grains start to orient towards similar directions, even if not they're very drastically different. So when all the grains start to orient along very similar directions, then there is definitely going to be an effect on um, the ductility of the material and the tensile strength as well. However, with very large strains, so when there's a change in processing conditions, etc., there's definitely going to be a change in, we are going to move from the elastic regime to the plastic regime as well. So which means um, between two processing conditions, we could have differences in the grain size, we could have differences in the grain orientations, etc., which can lead to tensile change in tensile strength, change in the ductility of the materials, etc. We could also have change in toughnesses too. Uh, Sometimes let's not assume all thermomechanical treatments to be at higher temperatures. Let's say when we expose a steel to very low temperatures, let's say sub-zero temperatures, then there is a possibility where this particular steel can undergo something called as a ductile to brittle transition, DBT. Okay. Uh, there are a lot of materials which can undergo transition. They seem to be ductile in nature, where they can undertake they are able to withstand a certain amount of plastic deformation. But when exposed to very low temperatures or very high strain rates, they are unable to withstand this treatments, this change in processing conditions, and their toughness is also compromised. However, what did we learn when we studied about, or when we understood about the um, uh, theory of elasticity and the atomistic nature of elasticity? Elasticity or elastic modulus depends only on the elastic modulus, or E, let's say. E depends only on the nature of bonding between atoms at a certain composition. Okay. When most of these processing conditions are not going to affect the composition of the material at all, unless and until there is a heat treatment, or there's a processing condition where there's going to be segregation of atoms, because of which there's going to be a change in the nature of bonding and the overall composition of the material. Uh, the Young's modulus of those materials is going to remain same irrespective of the processing conditions. Okay, moving on to the third question. The elastic modulus of most metal lies in the range of uh, it is in the range of 50 to 600 GPa. That is the we saw when we the very last slide of the class. Uh, Not necessarily this, but let's say germanium, tin, antimony, all these things had a GPa around 100, 150, 100 to 20 or 50 GPa in nature. I'm not including silicon and germanium because those are not necessarily. Also, most metals, as you can see, most metals is in the range of 100 to 600 MPa, 600 GPa, but in some cases it can go lower as well. So this the answer to this question is in the class, the last lecture of the class, the lecture 10, lecture 10. For metals, if we go down in the periodic table, then the elastic modulus, again, once we, as we discussed, when we go from carbon to silicon to germanium to tin to antimony, the elastic modulus seem to decrease. So it decreases. Again, why? The nucleus are of similar size, but the electron cloud grows bigger and bigger. The ability of the nucleus to hold on to the outermost electron keeps decreasing, and in these cases, we have a very, very shallow well. So when we have a very shallow well, then the elastic modulus uh, decreases. What will be the approximate value of elastic modulus of a material if the shear modulus is 150 giganewton per meter square and its Poisson's ratio is zero point 0.3? So what we need to find out here is shear modulus G is given. G equals, let me try to write it in new color. Yeah, I'm okay with this. G is given. G equals 150 Newton per meter square. We know the Poisson's ratio is zero point 0.3. We need to find E. So what is the relation between E, G and V? We know G equals E by 1, just give me a minute, E by 2 into 1 plus nu. Okay, we know the value of nu here, we know the value of G here, we can substitute, we can try and find out E. So E becomes, E equals G into 2, 2 into 1 plus nu. So which is 150 into 2 into 1 plus zero point 0.3, 1.3, just 150, oh, sorry, 152 into 2, we can change this as 300 already. into 1.3, which gives us 93. No, what is the value of this? Sorry, 13 threes are 39. Yeah, 390. So answer to this will be option D. We'll revise the relations here once again. G equals E by 2 into 1 plus nu. K equals E by 3 into 1 minus 2 nu. And then nu equals E by 2G minus 1. Okay, these are the three relations. Very, very important. If we know either of these two, we'll be able to find the third one. For incompressible fluids, the value of bulk elastic modulus is, what is the value of bulk modulus, which is kappa equals sigma hydrostatic divided by fractional change in volume. What they have given here is incompressible fluids, which basically means the fractional volume change del V by V naught equals 0. So any value that is, say, n by 0 is considered to be infinity, right? So when we have an incompressible fluid, the value of elastic modulus is infinity. Okay. Moving on to the next question. Three fluids 1, 2, and 3 have bulk modulus K1, K2, and K3 respectively. If K1 is greater than K2 and if K1 is greater than K2, which is greater than K3, then which fluid will have the highest value of compressibility? So bulk modulus K1 equals, let's say, uh, sigma hydrostatic is very similar. So then del V1 by V naught K2 equals sigma hydrostatic by del V2 by V naught, and K3 equals sigma hydrostatic by del V3 by V naught. Okay, we know that K1 is greater than K2 is greater than K3. When we have a ratio of K1 is to K2 is to K3, we will, so it basically becomes a competition between, because as the hydrostatic stresses, as we have assumed the hydrostatic stresses to be very similar, then it basically becomes a ratio of 1 by del V1 by V naught is to 1 by del V2 by V naught is to 1 by del V3 by V naught. So for K1 to be greater than K2, del V2 should be greater than del V1. Why? Let's just say K1 is to K2, which means V naught. Let's again assume V naught to be very similar. Just 1 by del V1 is to 1 by del V2. We are comparing del V2 by del V1, and it's K1 by K2. If K1 is greater than K2, for this equation to be greater than 1 or whatever it is, uh, then del del V2 should be, just to hold true, del V2 should be greater than del V1, right? So similarly, if we extend this logic to K2 is to K3 as well, then del V3 should be greater than del V2. So if we apply the property of commutativity, del V3 greater than del V2 greater than del V1, or K3 fluid has the highest value of compressibility because del V3 is the highest. So fluid 3 is the most compressible liquid amongst these three given liquids of um, compressibility K1, K2 and K3. Okay. The strong bonding in materials lead to low melting point. Strong bonding in materials lead to low melting point, high modulus of elasticity, low coefficient of thermal expansion, and low tensile strength. Uh, very strong bonding in materials does not lead to low melting point because, let's say, um, polymers, as we know, have low melting point, but and they don't have very don't have very strong bonding. Metals have a combination of metallic, ionic, and in some cases they do have some degree of covalent bonding as well. All three combined together. Same with ceramics. Ceramics tend to have ionic and covalent bonding. Ionic and covalent bonding. And we know ceramics have some of the highest melting points. We have metals like tungsten, niobium, tantalum, which have very high melting points. So given this, we know that strong bonding do not lead to very low melting points. They typically tend to have high melting points because it becomes so much more difficult for you to break the bond between two of these atoms and would drift them, make them drift apart. As simple as that. High modulus of elasticity. Yes, we know that the modulus of elasticity is almost proportional to the force in the potential energy versus distance plot. So when the force between these two atoms are very, very high, then the elasticity is also bound to be very high. Low tensile strength is a very interesting, which is not true. Again, because of very similar. Strong bond means we need to exert a lot more energy to go to maximum tensile stress and then uh, go to fracture. Low coefficient of thermal expansion, again very similar logic. If you think about it, it makes absolute sense. What is thermal expansion of coefficient? uh, Coefficient of expansion is nothing but the degree to which the two atoms displace or move away from each other as temperature increases. So for metals and ceramics which have a very high bond strength, you need to exert a lot more energy for you to be able to displace the two atoms again from away from each other, even by a certain very small amount. So low coefficient of thermal expansion is also a valid answer. In an experiment, ninth question, in an experiment, the bulk modulus of elasticity of a material is thrice its shear modulus. So K equals 3 times G is what we know here. The Poisson's ratio of the material is, okay, we know K equals E by 3 into 1 minus 2 nu, G equals E by 2 into 1 plus nu, and nu is E by 2G minus 1. So we need to find nu. We have, say, K and G, let's say. Um, let's just use this equation. K equals 3G, so 3G equals E by 3 into 1 minus 2 nu. We know that G is E by 2 into 1 plus nu, so we'll apply that as well. 3E by 2 into 1 plus nu equals E by 3 into 1 minus 2 nu. So E gets cancelled, 3 3s are 9. In this case, 9 minus 18 nu equals 2 plus nu. 2 plus 2 nu. Sorry. Yeah. Um, so 20 nu equals 7. Nu equals 7 by 20. Okay. So the answer is 7 by 20. Answer is option A. What will be the Poisson's ratio if the Young's modulus is equal to the bulk modulus? Here they have given the condition K equals E, but we also know K equals E by 3 into 1 minus 2 nu, which equals E. Then they've asked for the value of the Poisson's ratio. So um, 3 minus 6 nu equals 1 is the equation that we are presented with here. So 6 nu equals 2, nu equals 1 by 3. Yep, answer is option C, 1 by 3. Yep, right. What are the limiting values of Poisson's ratio? Um, we know Poisson's ratio is minus Ey by Ez, a ratio of lateral to longitudinal strain. And as you saw for metals, it is around 0.33. For ceramics, it is around 0.25. For poly, it is around polymers, it is around 0.4. So it is somewhere between the range of 0 to 0.5 for most cases. So let's say 0 to 0.5 to be the limiting values of Poisson's ratio. A bar of diameter 40 mm and diameter 40 mm and length 40 mm, 40 cm, okay, is subjected to an axial load of 100 Newton. Sigma axial. The bar elongates by 0.005 mm. The Poisson's ratio of the material of bar is, what is the Poisson's ratio of the material of the bar? The value is actually 0.33. Right now it's almost 9 o'clock. We don't have the time to solve this question. We'll try to solve this question in the subsequent class, or I'll try to finish this and then if time permits I'll come back to this question again. So the bar elongates, so we know that uh, del L equals 0.005 mm, and it is elongating along the length. So if this is the bar, this is 40 centimeter, diameter is 40 mm, axial load of 100 kilonewton, then actually the Poisson's ratio nu is minus Ey by Ez, or lateral strain by longitudinal strain. Lateral strain, as we know here, is uh, del L by L naught, which is 0.005 divided by 40 centimeter, which is um, uh, 10 power minus, sorry, okay, by 40 centimeter. Centimeter into 1 centimeter is 10 millimeters, so it's 400 mm. So this becomes just use my calculator. Zero point double zero 0.005 divided by 400. Okay, this is EY. There is going to be a shrinkage along its diameter as well, and not just elongation. But in order to do that, we'll have to do a conservation of volume. Volume conservation should, because as we know, uh, volume should be conserved, which means volume of cylinder is pi r square h. We know that the h has changed from V1 to V2. H1 has gone from 40, or L1 pi r square L. L1 has got from 40 centimeter to L2 is 40.005 centimeter, or probably even lesser than that, 005 mm. 400 mm to 400.005 mm. Okay. We know L1 and L2. We have to find the ratio of V1 by V2 equals pi gets cancelled, R1 square L1 by R2 square L2. We know L1 and L2. We know V1 and V2 should be 1. V1 by V2 should be 1. So R2 square L2 equals R1 square L1. Uh, R1 square is 40 mm. So R1 square by R2 square should be L2 by L1, which is 400.005 divided by, sorry, rather, R2 square should be 40 mm is, sorry, diameter. So 20 mm, 20 square into 400 divided by 400.005. Just 400 into 400 divided by 400 into 0.005, and R2 is the root of all these things. 400 into 400 is basically 20 root 2. Yeah, no, it's, oh, 400 root 1 by 400.005. It's some value. Okay, what will be the value? Well, the final answer is around 0.33. I'll do a better definition of clarifying all these things. I think I've gone wrong somewhere. I'm not really sure. Um, yeah, I can get back to you on in subsequent classes. Okay, the next question is, which of the following is or are true in the if the value of Poisson's ratio for a material is zero? The material is rigid, the material is perfectly plastic, longitudinal strain in the material is infinite, there is no longitudinal strain in the material. The answer is the material is rigid. Okay, if the value of modulus of elasticity and Poisson's ratio are 300 and zero point 0.5 respectively, the value of shear modulus would be, okay, shear modulus G equals E by 2 into 1 plus nu, right? G is E by 2 into 1 plus nu. E is 300, nu is zero point 0.5. Then G will be 300 by 2 into 1.5, 1 plus zero point 0.5, which is 1.5, which is 2 into 1.5 is 3, comes 300 by 3, which equals 100. Probably I'm assuming GPa. If I assume 300 GPa, 100. Final question, the potential energy of atoms at the equilibrium position is, what is the equilibrium position? So this is the potential energy versus distance plot that we are talking about. It's positive here, it's negative here, 0 here. We have a repulsive force here. Uh, we have an attractive force here. And then the combination of these two is drawn something like, okay, this is the point of minimum. Okay, the potential energy is minimum at the point of equilibrium. The point of equilibrium, the potential energy of atoms at this equilibrium position is minimum. Okay, okay. From today, we were able to solve. Um, we 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 had a revision of assignment one revision. We went through how to solve some of the homework questions like solving epsilon 2 prime 2 prime and gamma 2 prime 3 prime, along with, if we are able to understand these two with the problem solving class like epsilon 1 prime and gamma 1 prime 2 prime, we should be very well versed in writing the tensor notation of strains right now, strain tensors right now. We also went through the class notes quickly, week 2 class notes of atomistic theory, of elasticity, all these things. We were able to solve some problems from the second tutorial as well, the second week's tutorial as well. Uh, so time's up for now. Thank you so much everyone for attending. Thank you so much for listening to this. Please do comment if you have any feedback or if you have any further questions. Even if you don't, if you're not able to comment it out here, please do comment in the discussion forum for this coursework that we have. We'll try to take up a few more problems from the subsequent week. Again, next week we will try to solve. Try to revise assignment 1 and assignment 2 problems once again before we start with a recap of the subsequent classes, and then we'll try to solve some of the homework or example problems from next week as well. So I hope that everyone was able to learn something from this tutorial session, from this live session. Thank you so much everyone for attending. Uh, let us end this class. If you have any feedback, please do feel free to write it down in the comments. Please feel free to let me know through the uh, weekly reviews that you get. And thank you so much once again. I hope to see more of you in subsequent classes. Thank you.